All right, happy Wednesday again. Hope you're doing all right. All right, so before we get started on recursion today, I did want to show a PhD dissertation defense Monday the 5th via Zoom. If you're interested, model-based reliable mission planning of off-road autonomous ground vehicles under uncertain environments. Sounds really neat here, but you're welcome to attend either in person or virtually if this is your thing. I think you guys will be here on Monday. Might even be available because it's not till 10 to noon. I don't know, but it's an interesting thing. So there's this really cool picture of what it's like doing a PhD. I thought this was pretty fun. So if you had a circle of all human knowledge, by the time you're done with elementary school, you're the blue dot. By the time you're done with high school, you're probably around this green dot or so. You get a bachelor's degree with a certain specialty, you're this orange dot with kind of a bump on it. You get a master's degree, you kind of bump out that orange, turn this little red arrow here. Then you start the tough stuff. Read research papers takes you to the edge of human knowledge. Right? So finding all published research on a particular topic can take you to the bounds of human knowledge on that particular subject. Once you're at the boundary, you focus. Very, very tiny little spot here on what you're focused on. And you push at that boundary for a few years until one day the boundary gives away. And that little tiny dent you've made is called a PhD. But which is pretty cool, is that you've affected this circle of all human knowledge. So it's pretty cool, that idea that we can add new knowledge. And that's what that PhD is, that idea that it's a specialty you have added to the body of knowledge, something new, which is pretty cool. So that's neat. Anyway, that is Monday. So we're going to talk about recursion. Let me fire up PyCharm here. And then we've got plotting and basic graphics next week. Again, the goal is like half an hour to 45 minutes worth of content today, next Monday, next Wednesday, so you have time to work on the final project. I can answer questions. We can go from there. We'll have our last lab on the 5th. It'll be pretty short, again, so we have the bulk of lab time to work on the final project. And then we are presenting on the 14th, which I believe is Wednesday, right? 2 weeks from today. Is that right? 11:30 to 2:30. I don't think it'll take the whole time, because it's, ideally 5-minute presentations tops. I've never had anyone go more than 10. Like, they were really excited about their project, which is cool. Like, I like when people are excited about their stuff. So either individuals or partners, right, depending who's working. And if you're in a partner or working with a partner, I'd like both of you at least to say words. Like, you don't need to do a 50-50 even split, but you at least say something more than just, hi, my name is so-and-so as the partner. But you don't have to perfectly split it at all or anything there. So there's no points for the presentation. I think, did I put the rubric out here for this? I don't remember if I put the rubric out here or not. I didn't. I'm sorry. So we gotta put the rubric together, but there's no points for the presentation. But this is, if you don't present, I can't score it. Is that fair? So let's do our rubric here. So this is for our final project. All right, so we'll use this one for grading here. So we want probably just some broad categories are fine. So part 1, right? Blackjack classes. So just having the classes here, 10 points. So this is about design. So this is our good design or object-oriented design, right? So having the classes, so the classes can interact. They have private attributes with public functions. 10 points there, even if nothing else works. Okay, just having the classes there with good design, you get some points. We're a third of the way there. Okay. Next step then is being able to play blackjack interactively. So using my classes, or even if you don't use classes here, if you just can play blackjack, 10 points. Ideally, you wrote the classes first and then you play the game, but again, I guess that's up to you. However you want to earn your points here or not earn them, that's your call. So if you can play the game, we ask the user, do you want to hit or stand? Here's your cards. Here's what the dealer's card is. Do you want to hit or stand? 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 Eventually they bust or they stand. Then the dealer goes. Either they bust or they stand, right? Based on the dealer rules. And then we tell them they win, lost, or drew. Draw? Drew? Drawed? It's drew, right? I think it's drew. I'm really bad at English. And different words have different endings too that all seem the same. It's terrible. I get so confused. Trying to teach my kids English has been like the worst experience ever. It's like there's not good reasons. Okay, I guess the reasons are the different root languages, and I have no idea what root languages our words come from. Um, like you see the kids in like the National Spelling Bee, they're like, "What's the root language of this word?" They're like, "Oh, it's Germanic," and they're, "Oh, okay, it must be spelled this way." Like, how do you know this stuff? Of all the things in your head, but okay, maybe I'm just jealous because I'm a terrible speller. Right, so that's 10 points. The last 10 points then are doing the simulation and displaying result table. Simulation, there we go. 10 more points there, right? So that's the 100,000 hands, tracking our starting hand value, randomly picking hit or stand, tracking win, loss, and draw. So what happens when we do this? What happens when we do this? What happens when we do this? Okay, 10 more points there. That's the 30 points. That make sense? That sound good? No surprises here, I hope, right? Okay. And definitely happy to score partial points if it's not fully there. That's okay too, right? It's totally up to you. I'm sorry I don't have other grades in. I'm working on it. I think I got through a lot of our labs. I got to get back to the quizzes and the projects. Hoping to have that done next week. I know we're running short on time. I'm sorry. So sorry. I'm working on them. It's not the semester I had planned, but thanks for bearing with me. All right, should we talk about recursion? Okay, so recursion is actually pretty simple here as a idea here. So this is recursion. Is it week 14 recursion? We'll call it that. In that recursion is defined by a function that calls itself. So in your study of mathematics, you might have come to recursive functions here. The most famous one here is Fibonacci sequence. This is a essentially recursive formula here. Where's a good, we'll just take the Wikipedia link. That's probably fine. Fibonacci, the 0th number, right? Even math starts at 0. How awesome is that, right? Index 0 is 0. Index of 1 is 1. Any other Fibonacci of n is defined as the Fibonacci of n minus 1 plus the Fibonacci of n minus 2. Right? So we get a sequence here, 0, 1, 1, 2, 3, 5, 8, 13, 21, where each number is the sum of the previous two numbers. This number is the sum of the previous two numbers. That's the definition of it. And it makes this really cool, what is that, the golden ratio rectangle here as you go, which is pretty cool. So like it's a fun sequence here. Later when I have more time. Stop. Fine. Remind me later. Now will you go away? Okay. Right, so going on up and up and up and up and up. It's pretty easy to define. So when we want to define a function for Fibonacci, now I'm bad at spelling, so I'm just going to call it fib. Is that okay? And you have to tell me the nth here that you want. So you tell me what nth Fibonacci number you want, I'll give you the number. So we can check real quick. Hey, if nth is equal to 0, return 0. Now if nth is equal to 1, let's return 1. Now, hopefully you're thinking we could combine this here, right? Probably could combine it. That's okay. You might also be nice here because people will give us really dumb things too. I could say, hey, if it's less than or equal to 0, let's just return 0. So if you give me a negative nth, I'll just give you 0 back and tell you to go away because I don't really know what to do with it otherwise. Like you don't have negative Fibonacci sequence numbers. It just doesn't work. So I'll just give you 0. So this was pretty easy here. Now, if it's not 0 and it's not 1, right? Our mathematical definition is it's nth minus 1 plus nth minus 2. So we're going to return fib of nth minus 1 plus fib of nth minus 2. That's it. We have now solved Fibonacci. Right? What happens here is this function will call itself. Right? So I'll say for n in range, let's just go like 20 here, right? Let's print fib of n. Right? So when n is 0, we should get 0. When n is 1, we should get 1. When n is 2, we should get, well, it's not 0, it's not 1, so we should get 2 minus 1 fib, right? And fib of 2 minus 2, and on and on and on. right? So if I put this in debug mode here, so we can watch it run, this is really fun. I'll put a breakpoint in and hit debug. We now get nth is 0, right? So we're asking for the 0th Fibonacci number. If I step over, right, n is less than or equal to 0, we'll return 0. Pretty easy, we'll print 0. Now n is 1. We call fib, give it n is 1. N is not 0, less than or equal to 0. N equals 1, return 1. Pretty easy. Now n is 2. Now this is where it gets interesting. So n is 2. It's not 0, it's not 1. We're here. So what's happening, we're in Fibonacci, right, at line 6, where n is currently 2. Now, I don't want to step over. I want to step into here to make sure I'm going into my function call. If I step over, it's just going to run it and be done. Or actually run to the next breakpoint, but stepping into is what I want to do here. So I'm going to step into my code. So it's going to say, okay, hey, I want fib of nth minus 1. So we'll step into. Now we have this call stack. So remember, Python remembers where it was when it left off. So it was at line 6 where n was 2, nth was 2. Now it's at fib line 2 where nth is 1. When this is done, it'll come back to where it left off here and just keep on going. This is called the call stack, right? Every time we call a function, it gets added to this call stack, and it just takes care of them top to bottom. So we step now, we get 1, we return a 1, great. So now we're back to fib of line 6, right? Where nth was 2, we're step into our code. Now we're at the fib of nth minus 2. Fib of 0, we get 0, great, we're done. We're back to here of line 6. We step over, we got back our result. We're done. Now n is 3. Step into our code. Okay, n is 3. We'll step. It's not 0, it's not 1. So let's step into. So it'll be fib of nth minus 1. 3 minus 1 is 2. We'll step into. Now nth is 2. Okay, well, we know nth of 2 is going to go run nth of 2 minus 1. Now we're at nth of 1. So we have 3 different calls to fib on our call stack here. Right? This is recursively calling itself over and over and over and over until it finds a solution. This idea here, these solutions are known as base cases. The base case is the simple form of a problem that has a known solution. So with a recursive function, you have to have a base case. You have to know, hey, this is when the problem is solved. The other thing you have to be able to do is take a complex problem, something that does not add a base case, and simplify it, make it approach a base case. So, okay, I don't know how to solve fib of nth of 3, but I do know I can turn that into fib of 2 and fib of 1. Add those together. Fib of 2 doesn't have a solution, but I can find it by taking fib of 1 plus fib of 0. We'll do that. So we can take a complex case that doesn't have a solution, break it down into smaller and smaller and smaller steps until it hits one of these base cases that does have a solution. That's what we're doing here. So eventually we'll get our solution here. We'll see, okay, we took care of that one. Now we're at of 2. We'll step into our code. Now we're at fib of 1, right? So we're at nth was 3. We did fib of 2. Now we're at fib of 1. We get our solution here. We're ready to return our result. We're done. Now fib of 4, and on and on and on. So this one gets a little boring here. Let me take this breakpoint out and step over a couple times to look at, say, let's keep on going here. Let's try 15 here. 15 will be fun. So I'm going to step into 15. Now we're going to step into, fib of nth of 12, nth of 11, nth of 10, nth of 9, nth of 8, nth of 7, nth of 6, nth of 5, nth of 4, nth of 3, on and on. So we have this big call stack here, right? Where nth was 15, and then 14, and then 13, and then 12, and then 11, and 10, and 9, on and on and on and on and on, right? Eventually we'll get down to a nth of something we know the solution for, and we'll be done. Okay, so it just works, which is pretty cool. So if I just run my program, we'll see we get some fib numbers pretty quickly here. Computer's pretty quick at this, right? Now the problem is if I start cranking this up here, and I want to go to like 40, let's do 45. We'll run this here. So we get some numbers pretty quick. And now you see it's starting to slow down here. Okay, let's print our nth here because I want to know what it is. So this is f string. This will be my n, and I don't know, just sure. And then the fib of n. And I want to see what the particular values are here, right? There we go. run that. Here we go. So it starts to slow down around 31, 32, 33, and you notice it's going to get slower and slower and slower as it goes. Because what's happening behind the scenes is it's literally adding 1 this many times. So I've now added 9 million ones together, 14 million ones together, because the only answer I can ever get is a 1 or a 0. And it does it. The computer's happy to do it. It just takes a little while here. So in terms of performance, this is really slow and really bad, right? Like, I'm still waiting here. All right, I've added up 39 million ones now. Let's go. And I think you can imagine why this is slow, because you saw when I did, 15, I had 14 and 13 and 12 and 11 and 10 and 9 and 8, that many function calls. But then for each of those function calls, it gets worse, because fib of 14 will spawn fib of 13 and 12 and 11 and 10 and 9 and 8, 7, 6, 5, 4, 3, 2, 1. That fib of 13 call will call 12, 10, 11, or 12, 11, 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. And that one will call, so it really branches out exponentially. Probably even factorially. Is that even a word? Factorial amount of growth here of function calls. So we're still running. I haven't even got there yet. And we're only at 63 million. So it's 63 million function calls that had to happen here to calculate this value. So just because we can do something recursively does not mean we should do it recursively, right? There's a fun, we can just let that run while we chat here. So really, any problem that can be solved with recursion can be solved without recursion. The reason why we like recursion is it helps us, it's kind of a natural way to think about some problems. So imagine you have a computer, like I have here, and it has a C drive, and it has a users folder, and it has a documents folder here, and it has a GitHub folder, and so on and so on and so on. How would we go from this folder and find all the subfolders, and find the subfolders of subfolders, and find the subfolders of subfolders of subfolders, and find the files inside of subfolders of subfolders, and how would we do that? Like, without something that's a recursive nature. Right? It's pretty easy. When we looked at that OS walk function, OS walk gave us directories, gave us subdirectories, and we could walk each of those, and it would just go through the entire path for us. That's recursion. It says, okay, if I'm a directory, give you all my subdirectories and files. And when I go to that subdirectory, okay, if you're a directory, give me all your directories and files, all your subdirectories and files, and just keeps on going. So recursion is a natural way for us to look at certain types of problems here. Works out really well for certain problems, which is pretty fun. So there's a puzzle you might be familiar with called Sudoku. You guys ever played Sudoku? I'm so glad you do. I like Sudoku as well. So with Sudoku, you get a grid of 9 by 9, and you have to put the numbers 1 to 9 in the grid. Now each row have the numbers 1 to 9, each column will have the numbers 1 to 9, and each minor grid here, these 3 by 3 boxes that there are 9 of, will have the numbers 1 to 9. And you can do this with, right? And if you're able to do it like that, there are no repeats, right? You never have the same number twice in any column, in any row, or in any grid. And that's the puzzle. And you can solve it. You can use logic to deduce these things. Now, it turns out I'm bad at logic. Okay, I'm not bad at it, but like some of the hard Sudoku puzzles are really hard, and I can't solve them. And it frustrates me. But I wrote a computer program that can solve Sudoku puzzles. And I told my wife, hey, look, I solved it. She's like, you didn't solve it. The computer solved it. I said, well, I wrote the computer program to solve it. Doesn't that count? And she said, no. I was really sad. I'm a little torn because it is cheating. It's cheating. It's cheating. So if you're not good at logic, like some people here up front, the easy way for you to solve this, and maybe easy is the wrong word here, but what you would do is you would find the first open box here. So this first open box right here. I would say, can I put a 1 here? No, I can't, because there's already a 1 in this grid. Can I put a 2 here? There's no 2 in the row, or no 2 in the column, no 2 in the row, no 2 in the box. Yes, I can put a 2 here. I'll just pencil in a 2, and maybe I'll come back to it later. So I'm going to know that, hey, at this, remember, indexes start at 0, so this is 0, 0, right? I put a 2 in, okay? Then I'm going to go to the next box, so now I'm at 0, 1. Can I put a 1 in? No. Can I put a 2 in? No, there's already a 2 here. Can I put a 3 in? No. Can I put a 4 in? No. Can I put a 5 in? Yeah, 5 looks fine. I'll put a 5 in. I'll go to the next open box. Okay. Can I put a 1 in? No. A 2? No. A 3? No. A 4? No. A 5? No. A 6? Yeah, I can put a 6 in there. Sure, let's go for it. The next open box. So that is 0 and 0, 1, 2, 3, 4 here. Okay. Can I put a 1 in? No. Can I put a 2 in? No. A 3? Yeah, 3 looks fine. Let's put a 3 in here. Go to the next open box. 0, 5. Okay. Now we're at this box. Can I put a 1 in? No. A 2? No. A 3? No. A 4? No. A 5? No. 6? Yeah, 6 looks okay. Oh, nope. We put a 6 in already at this spot, so we can't put a 6. How about a 7? 7 looks okay. Put a 7 in. Go to the next open box. So it's 0, 6. Can I put a 1 in? Sure, put a 1 in. All right, go to the next open box. 0, 7. Can I put a 1 in? No. How about a 2? No. A 3? No. 4? Yeah, 4 looks okay. We'll put a 4 in. I'm sorry. Right? All right, go to the next open box. So now we're at row 1, column 0. Can I put a 1 in? No. Can I put a 2 in? No. Can I put a 3 in? No. 4? No. On and on. Eventually, I'm going to hit a place where the answer is no. Let's pretend it's right now, because I lost track because I didn't actually write these things down. Is that okay? So we'll say the answer is no. If I can't place a number here, I'm just going to go back. I'm going to backtrack and say, okay, well, that was no good. Let's go back. The last thing I did then was put a 4 here at 7. Say, obviously, that didn't work. It can't be a 4. How about a 5? Can it be a 5? No, there's already 5. Can it be a 6? No. Can it be a 7? No. Can it be an 8? No. Can it be a 9? No. Well, that one's no good either. So undo that one. Go back. Okay? Can't be a 1. How about a 2? How about a 3? So we're just literally trying every single possible solution that there is, just brute forcing it. And if it doesn't work, we backtrack. This is using recursion. It's a recursive backtracking solution. We just try every single possible thing. If we get stuck, we undo. Eventually, we'll find a solution. This works with Sudoku solving. It works with maze solving. Right? The idea, if you have a maze here, so we just build like a little maze. Let's just look at like an example maze here. Simple maze with grid. See if we can do this here. Here we go. This is kind of a big maze, so that's okay. It's got a grid. So I'm going to start at the entrance square, the start square. Okay. Now my algorithm, my steps to solve this here are the different options that I can do. Right. I can go up, I can go down, I can go left, and I can go right. Any really order that you want here. Doesn't really matter here. So what order do you think is best here for up, down, left, right? Do you care? Up, down, left, and right? Let me zoom that in a little, sorry. Okay, so we'll say that's our algorithm, is up, down, left, and right. Okay, what's the base case for solving a maze? How do we know if we've solved a maze or not? If I got to the end? Sure, so imagine there's like a start mark and an end mark here. So my base case is, did I get to the end? The end square. If I did, I'm done. Okay, this is my base case. Okay, if I didn't, then I'm going to try up, down, left, and right. Try and simplify the problem. Take a complex problem, one that doesn't have a solution, make it approach a simpler case that might have a solution. So we're going to be here at 0, 0. Can I go up? We're at 0, 0. Can I go up? No. We did that one. Can I go down? Sure. Let's go down. So now I'm at 1, 0. Can I go up? Uh-oh, I can. So we probably have done a bad thing here now. If I go up from here and go back to 0, 0, we're just going to be in a loop, up, down, up, down, up, down, up, down, up, down. So that's no good. So when we're solving our maze, we need to be Hansel and Gretel, right? This idea of going somewhere needs to involve putting a little breadcrumb down so that you don't, actually, it's like the opposite of Hansel and Gretel, right? We don't want to step on our breadcrumbs. We don't want to follow the path home. We're not trying to get home. We're trying to get to the end. So if we leave a breadcrumb there at 0, 0, I won't repeat. I won't go back there. Right? So we can leave a little breadcrumb there and not step on it. So when I say, can I go up? I would say I can't step on breadcrumbs and I can't cross walls. That sound fair? Okay, so we can't go up because it's a breadcrumb. Can I go down, left, or right? Well, yeah, sure, I can go down. Okay, how about at 2, 0 then? Up, down, left, and right. I can't go up. I can't go down. There's a wall. I can't go left, but I can go right. Let's try going right. Okay, sure. So now I'm at 2, 1. I'm going to try up, down, left, and right. I can't go up. There's a wall. I can go down. Let's go down. So now I'm at 3, 2, or 3, 1. Right? We're at this square here. I can't go up. I can go down. So I have down, left, and right. Now I'm at 4, 1. Can't go up. Can't go down. Can't go left, but I can go right. Right? So I'm like marking these off my list here: up, down, left, and right. I can go right. So now we're at 4, 2. Right? We're at this square. Can't go up. Can't go down. Can't go left, but I can go right. Now at 4, 3. We're at this square. Can't go up, can't go down, can't go left, can't go right. We've reached a dead end. We need to undo. We're going to backtrack. So, okay, this comes off the call stack. All right, well, I tried right. There's nothing left to try. Undo. Backtrack. I tried right. Can't do that. Backtrack. All right, well, I tried down. That was no good. Now try left. Well, I can't go left from here. I can go right from here. So let's go to the right. So now we're at 3, 2. Right? It's just this naive backtracking solution. It's just going to literally try every single possible path to find a solution. And it works. Now, this is not a good maze solving solution here, right? If you take the AI class, last I heard, one of the basic things they start with is maze solving, or path finding. Sorry, not maze solving, but path finding. How do you get from one path to another? There's some well-known basics of path finding that are kind of fundamental to AI, which is really interesting. So you'll learn all about that later on. That's a fun one. So recursive solution is not ideal because it's literally trying all sorts of different options here, and they might not work. Right? We might be able to know that it's a dead end. Like if I just as a human look down this path, I can quickly see it's a dead end. The computer can't look ahead, right? It doesn't do that. Or at least our algorithm doesn't look ahead. Our algorithm says try it here. Go for it. There's a saying that's been pretty popular now. You something around and find out. But have you heard of that one? That's what our solution is doing here. It's just effing around and finding out. It will find a lot of dead ends, but it'll find a solution. Right? So it works. This idea of backtracking recursion. It's basic, but it works for us. So do you want to do maze solving or Sudoku today? Sudoku? Okay. So we'll do Sudoku. So we can write a little Sudoku solver here. So I'm going to add a new Python file. We'll call this our Sudoku solver here. We're going to write a class for Sudoku solver. Sudoku solver. We're going to define an init method here. So I can solve any, what do we want to call that, like grid here? Just call it a grid. If you give me the grid, I'll go solve it. So I'll say myself.grid is the grid. I assume this is some two-dimensional or 9x9 2D list, right? List of values here. That's what it should be here. Okay, so I'll accept the grid because I need to have the reference to it. I need to store that value here. Then I'm going to go and solve. We'll call self.solve. Okay, that's it. So in my solve function here, I need to do a couple things. Right? I need to find the first available row and column, or the next available row and column. So we'll have a row and column then, or how about row index? It's probably better, right? And a column index equal find next open space given, self.find next open space. So if we can find the next open space, we can get the row index and column index, right? From there, we're going to take the number. So for number in range 1 to 10, remember, because we want 9 inclusive, but you don't get the last value in range. So ranging 1 to 10 will give me 1 to 9 here. Let's try the numbers 1 to 10. We'll try and put those in. Right now, if our grid here then is all numeric values, it works well. If it's string values, it's a little bit different, but we can try numeric values, and I think it'll work okay. It'll print nicer if we use strings, actually. So it might be nice to use strings instead. I will say so number equals string of number, just so that I can deal with strings. Printing a blank it's easier to print a space than it is to print nothing. Like it'll line up nice on my grid here when I go print it here. Okay, so for numbers 1 to 9, right? Let's go try it. So if self.can place number given the number, then we'll take our grid, self.grid, at the row index, at the column index. Remember, so if with a two-dimensional list, a list of lists, takes, this is the row, and then this is the column inside of that row. Here, we'll assign the number, right? If we can place. Okay. And now I think all of this we forgot our step here. So we're going to say if not self.solved or is solved. So if we're not solved, let's keep on going here, right? So that if we haven't reached a base case, what's the base case for Sudoku? How do we know when we're done? When there's no spaces left, right? There's no empty spaces. If you have a number in every spot, you're done, right? So that's our quick little check for the base case. So if it's not solved, we'll go find the next open space and go do the thing, put the number in. Once we've put a number in here, right? If we can place the number, then we need to recurse. We're going to call self.solve. Right? Go to the next step. Find the next open space. Try the next number. Right? Try number 1. Try number 2. Try number 3. Try number 4. Try number 5. Right? When that's done, if we come back from solve here and we haven't finished, we need to undo. Right? That idea of let's erase this mark. That one didn't work. So if I call solve and I get stuck, when solve is done, I can say if self.is solved or not self.is solved. Is that funny? We keep putting not here. So how about we say like is unsolved? How about that? Because we're writing our functions here. So we can say if unsolved. If we're unsolved, then we're going to undo that mark here, put ourselves back to an empty space. Right? If I got stuck somewhere, I called solve and I couldn't place any more numbers. Right? I tried the 1, I tried the 2, I tried the 3, I tried the 4, whatever. I need to erase it. So if I'm not solved, erase that number. Then I go back to my for loop. Okay, well, I tried number 1, that didn't work. Let's try number 2. If I can put a 2 down, put the number 2 in. If I call solve and I'm not solved when I'm done, erase it. It was no good. Right? That's it. That's our Sudoku solver. That's the entire algorithm here. Because it does backtracking recursion. It recurses and it backtracks. It undoes when it gets stuck. Okay? Then we want a function here for, I don't know, how about just print? Or how about self is string? We'll override string, right? Because we can do that. String of self. So we're going to build a string. So we'll have our grid string starts off as blank, and then how about for row in grid? I'm going to take our grid string, and we want to append to it row as a string plus a new line character, or self.grid. Sorry, self.grid here. Then we're done. We can return the grid string. There's a way to do this in a list comprehension. I think you can do it in a single line. Maybe we would join these together. Oh, let's do that. Let's join it here. So we'll return. We want a new line character dot join my self.grid. And we need each of these. So we need string of row or row in grid. There we go. I think that'll do it. So for each row in the grid, turn yourself into a string, then join with new lines. It's okay if we have to look it up. It probably will fail, but that's okay. We can try it. Okay. What's not done though is these next steps. So these should actually probably be private functions, right? I don't want these to be public functions. So let's make these private functions, right? So no one else is going to call them here. Then we can write some functions in our class. Self.define is unsolved, right? So we're unsolved if we find a space. So we can say for row in self.grid, if there's a space in row, return true. Right? If we find a space in any row in the grid, return true. We are unsolved. If we've gone through every row and we haven't returned true, return false. We are not unsolved. Right? Not unsolved means you're solved, but like the way we're using it, I think makes this a little bit nicer to say unsolved. we could have flipped around either way. Does that make sense? Okay. How about I define bind next open space? Now this one here, we need the indexes because we need to return the row index and the column index, right? So we're going to say for row index in range length of self.grid, and then for column index in range length of how about row self.grid. That's probably fine because we know it's a square here. I don't know if you can actually do Sudokus that aren't squares. They probably don't do rectangle ones. That probably doesn't make any sense. So it's probably safe to call this a square. We can say if self.grid at the row index at the column index is equal to a space, we'll return my row index, column index. Right? The first space I find, return. That's it. This doesn't really work if I don't have a space, but again, we don't really care. We'll just return nothing, return none, and it's probably fine. Right? That's it. So let's make a Sudoku puzzle. How about a grid here then? Equals, so it'll be a list of lists here, right? So we need spaces 1, 2, 3, 4, 5. Oh my goodness, I can't hit the right keys. 5, 6, 7, 8, 9. Right, so there's 9 blanks. We need 9 of these rows. 2, 3, 4, 5, 6, 7, 8, 9. We don't need the last column or comma. Okay, let's put some numbers in. Did I lose my Sudoku? Here it is. Font, images. Let's just find a Sudoku puzzle here. Sure, let's do this one. So we'll shrink that down. Okay, so we have a 5, we have a 3, we have a 6, a 9, an 8. Let's go over here and do 8, 4, 7, 6, 4, 1, 9, 8. Oh, those are, yep, thank you. Just take out an extra one over here. Oh, goodness. Insert mode. All right. 4. Oh, yep. 8. Space. All right, and then a 2. I keep hitting the wrong keys. It's killing me. 6, 8, and a 3. We'll call that good enough here for now because our program can solve it without more hints here. Right? So we make a Sudoku solver. So this is my puzzle equals a Sudoku solver given the grid. And then we can print the puzzle. Right? It should be solved. Right? Let's run it. Oh goodness, we broke it. Sudoku solver has no attribute can place number. Oops, did I do the function wrong? Oh, we didn't do a can place number. That's the last part. We didn't do this part. Sorry. One more step. So define self can place number given a number. Okay. Now, oops, we probably need to tell it also what row index and column index. Row index and column index. So can I place a number at a given row and at a given column? Right? So this one is 3 different steps, essentially, right? So we're going to return can place number in row given the number and the row index, right? So self dot, right? That and self can place number in column given the row index and column index. We need our backslash. There we go. And one more. Can place number in grid. Right? Or like, I don't know, square? How about square? Square. Probably actually don't need the row index for the column, right? We just look at just the column here. So can I place it in the row? Can I place it in the column? And can I place it in that 3 by 3 square? Okay, so it's just adding all those together. I have to be able to do it in all three for that to work. All right, we're doing our functional decomposition. Did any of you use that term at Thanksgiving and have everyone look at you funny? Be like, nerd. No? Your families know you're nerds, right? Not a surprise. Like using funny terms like functional decomposition shouldn't phase them. No? Okay. This is can place number in row given the number and the row index. Now this one's pretty easy here. Oops. We're going to return number is not in self.grid at the row index. Right? If the number is not in the row, we can place it there. Right? Okay. Can place column. Can place number in column given the number and the column index. Now this one is a little slower here, but that's okay. So we're going to say for row in self.grid, if number is equal to the the row at the column index, return false. If we find it in a row, tell you no. If we've gone through every row and haven't found it, we're going to return true. Yes, you can. Right? Go through every row at that column index. If we haven't found it, yes, you can place it there. Okay? Can place number in the square. This one's a little trickier here, but we can do it. Needing self, right? Number, row index, column index. Now, this one here, I've done this a couple times, so I'm sort of familiar with it here. But what we need to do is I need to look at a 3 by 3 grid based on a location. So if my row index is 0, 1, or 2, I need to start at row 0. If my row index is 3, 4, or 5, I need to start at row index 3. If my row index is 6, 7, or 8, I need to start at row index 6, right? To find the top corner of the grid. Same with the columns. Columns 0, 1, and 2, I need to start at 0. 3, 4, and 5, I need to start at 3. 6, 7, and 8, I need to start at 6. So we need to find the starting column and the starting row here. So to do that, it's some arithmetic, right? So we're going to have a starting row index is equal to my row index modulus 3. So row index 0, 1, and 2 will mod to 0. Row index 3, 4, and 5 will mod to 1, but I really need that to be 3. So mod 3 times 3. So 0, 1, and 2 hit 0. 0 times 3 is 0. 3, 4, and 5, mod 3 is 1. 1 times 3 is 3. 6, 7, and 8, mod 3 is 2. Times 3 is 6. So now I'm getting my 0, 3, and 6, right? Same with the column index. Starting column index is my column index mod 3 times 3. I've done this a bunch of times. It's okay. You would figure out the arithmetic if you wrote it down. I promise you. Okay. And then I'm going to say for this is row index in range of my starting row index to the starting row index plus 3. Right? I want to range from wherever I'm starting here to that plus 3. So I'll get 0, 1, and 2, or 3, 4, and 5, or 6, 7, and 8. Right? And do it again now for column index. Column index using my starting column index to starting column index plus 3. Right? Range through. If my self.grid at the row index at the column index is equal to the number, return false. If I've done all of that, I've checked all 3 by 3, right? I'm going to return true. Yes, I can place it there. That make sense? Okay, now I think it'll work. Let's try it here. Uh-oh. Something's not working right. I think it's stuck. Where did it get stuck? There's the number. Okay, that's all right. We'll run in the debug mode. Oh, here it was. Can place number. Line 39 was stuck at can place number. Really? Return can place number, can place number, can place number. All right, that's all right. So let's run it in debug mode here, and we can pause it when it gets somewhere here. So we should be able to see our current grid here then, right? So we filled out a bunch of them here. So we're currently at this call here, right? Where you can look and see all the different calls to what our row index and column index is. So we're currently at row number 6, row index is 3, column index is 1. So we're at row 3, column 1, trying number 6, right? We're checking to see if we can place the number. So we'll step into our code, or we'll step over here. Oh, I wanted to step. That was wrong. All right, we got a little farther here. So let's keep going. Let's continue on for a little bit. And then pause it. You know, maybe I do need a couple more numbers here. I wonder if this is going to go. It's just going to be slow. Let's put a couple more numbers in our puzzle and see if that helps. There's just a lot of possibilities here. I wonder if it's just getting hung up on that. Okay. Shoot, that was too much. All right. So let's see our 7. We go here, right? 9, 5, and 1. And then over here, we'd put a 6, 3, 1, 6. All right, let's try a couple more numbers, see if we can get a solution. There we go. Oh, uh-oh. Maybe I put it in wrong because we're getting, it's all getting undone. Because this is what we gave it, right? It's the blank one. Let's try this. Let's see if it is solved. Let's put an else in here. Else, we'll print self. See if we get a solution here. Nope. All right, so it can't solve. Do we give it something invalid? Did I mess up what we gave it here? We must have messed it up. I feel like we messed it up somehow. I think we did it. 5, 3, 6, 9, 8, 8, 4, 7, 6, 7, 1, 9, 5, 6, 8, 3, 2, 4, 1, 9, 8. Oh, it looks okay. 6, 1, 3, 6. Is this a bad puzzle? 2, 8, 5, 9, 7. No? Oh, we'll run into debug mode, see what happens. Let's try it again. I think that should have worked. That's okay. There's our grid. We'll try a bunch of numbers. Let's just go for a while here and see if we can, how far we get. Step out, step out. So it should be working on the grid, putting more numbers in. See how far we get. Let's see. Get to there. Oh, I got another idea. So let's do this. So every time we call solve, we can just print ourselves here. Print self, and then we'll print just a blank line. So this will be a lot of output here, but we can kind of see what's happening and see how far it gets before it gives up. Right? Oh, it didn't get very far. Look at that. So it started, so it got through 4 and then gave up. Something must not be right with our logic here then. Right, because it couldn't put any more numbers here. Should be able to do a 1. Right? Number, string of number, can place the number. All right, that didn't get super far, so let's try that here. So let's put a breakpoint in here, and I want number equals 1. Let's try that. Okay, so skip that one, continue. No? All right, I must not have done this right. We're so close, so close. All right, can place number, that's fine. It's fine, step out, step out, step out. I keep looking at this grid here. Oh, that one. Can remove watch. So 7. Okay, so we have the 4. So this would seem like where we're stopping before. So now what is number? Number 6. trying to put a 6 at column 6. So 0, 1, 2, 3, 4, 5, 6. Okay. Column 6, number is 6. Can we put a 6 in here? Because 1, 2, 3, 4, 5 was no good. Right? So we shouldn't be able to put a 6 here. That should be false. So we can't put a 6. Now number should be 7. Let's check to see if we can put a 7 in. Can we put a 7 in here? No, we can't put a 7 in. That one's no good. We should undo. Can we put an 8 in there? I think. Can we put an 8 in this grid? Nope, because there's one down below, so we shouldn't be able to put an 8 in. All right, for 9, can we put a 9 in? There's no 9s in that row. Were there any 9s in that column? I don't think we had 9s in that column, did we? So 9 should be okay, right? In this column? Let's step into our code. So can we place in the row? Is 9 not in the row index? And then we'll step into 9 is in the column, right? Check every column here. Shouldn't return false anywhere. Step out of that one, and then last step into, okay, in the square. So maybe that's where our problem is, into the square. So it should be this last row index and column index, right? So starting column index is, 0. That's not right. What column index do we tell it? Column index was 6. What did we do wrong here? 6 mod 3 should be 2. 2 times 3 should be 6. Do we need order of operations? Should have done that. What if our order of operations is wrong here? Let's see. That is the problem here. So if we fix that value, I think we can change that. Starting column index, we want to be 6. That value is 6. We'll change the value. This was fun with debug mode. So it works if we calculate that right. That's interesting. All right. Let's try it one more. Let's just run it here, see if it solves. No? All right, well, it's definitely here. Our column index mod 3. Am I not doing the right thing? Oh, let's try it. Let's try breakpoint here with debug mode. All right, so we'll step out. We don't need this one here. See how far we can get in this grid. Step out. We should be able to place a bunch of numbers, and we'll get down to where we have that. Okay, so now we have our 4. Okay, so we're trying the 6 here. Right, if we can place a 6 in the grid. So our row index is 0. The grid column index is 6. Number 6. We should get 6 mod 3. Starting column index 0 again. Is this not doing? Am I crazy? That works, right? It's supposed to work? All right, hang on. Let's try this. 6 modulus 3. Is this not the modulus operator? Am I confusing things in Python and other languages? Shouldn't that give me? It's not mod. No, no. Oh, goodness. We don't want modulus. That's the remainder. My arithmetic is bad. No, we want integer division. Integer division, not the remainder. You folks have to tell me when I'm stupid. Come on. All right, I've done this arithmetic a lot. Not enough, I guess. Okay, so integer division divided by 3. 0, 1, and 2 is 0. 3, 4, and 5 is 1. 6, 7, and 8 is 2. Not modulus. Eric's dumb. Okay. Maybe that'll fix our problem. I'm going to take out this print here because I don't want it to print every single time. Just for fun. And I think we can get rid of that one. Hopefully that's it. Let's see if that's it. Yay! We solved it. Now I feel a little bit better. And we can check and make sure it's good, right? We have 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. I think it's okay. All right, well, that was fun. That was debugging. I totally did that on purpose to show you what debugging's like. No? You don't buy it? That's okay. All right, so this is just an example of recursion. Now, we don't need recursion to solve this problem, but this is harder to track without recursion. Like, how do we track what we're in, what number we're trying, what solve position we're doing? It's doable, but it's tricky. Now, back to the Sudoku example, though. Or, I'm sorry, the Fibonacci example. This we don't need recursion for. We can write a better fib, and this will be the last thing we do, is a better fib here, given an nth. And we get to do a loop, right? So we can have the nth of, I don't know, minus, okay, we'll take our first steps here, because these are the same. And if we're not there, we'll start adding up. So I'll have a current nth is 1, right? So if we're not nth of 0 or nth of 1, we're going to be at 1, right? And then we can say, while my current nth does not equal the nth here, right? I need a previous value, so I'll have a previous value is 1, and the current value, current is 1, right? As long as we're not at the nth, then let's keep on going. So if I'm not at the nth value, I'm going to take my next, right? It'll equal the previous plus the current. Then my previous becomes the current, and the current becomes the next. Now my current nth goes up by 1. When I'm done, I can return the current value. Right? We just loop. As long as we haven't gotten to our nth value, let's add up the 2 before. That's my next value. Change the previous and current, and then add to the current nth. So when nth is 1, right? 1 is not 2. We would add up 1 plus 1. Now current becomes 2, add to the current, and we're good to go. So I can use my better fib here, right? It's just a loop at this point, and I can run this one. Oops, this one here, and see how fast that was. Python's much faster adding up than it is adding ones here, right? So it doesn't have to be a loop, or I'm sorry, it doesn't have to be recursion if it's just a loop. Now the Sudoku solver, those more than just a loop, because like we're tracking the current number, and then we have to track our undo steps, and it's a little bit trickier here to solve it without recursion, but you don't have to use recursion. Not the only way to solve it. So the rule is anything that can be solved with recursion can be solved without. There's another great puzzle here. This is the Tower of Hanoi. Hanoi animated. This one's pretty good here. Towersofhanoi.info. Yes. So the idea here, we want 3 pegs and 7 disks, is you can't place a bigger disk on top of a smaller disk. But what you have to do is you have to move all the disks from one peg to another peg. So this is a very easy solution with recursion, because can you move disk 7? No. Can you move disk 6? No. Can you move disk 5? No. Can you move disk 4? No. Can you move disk 3? No. Can you move disk 2? No. Can you move disk 1? Yes. So the simple piece here is moving one disk. To move one disk, I just move it to the other peg. To move 2 disks, I have to move one disk, move the second disk to the peg I want it to go to, and then move the one disk on top of the second disk. So moving 2 involves moving 1, moving 2, and then moving 1 again. Moving 3 disks involves moving 2 disks to the peg I don't want, moving the 3rd disk to the peg I do want, and then moving 2 disks back on top of the 3rd disk where I want them. Right? So if we show the animation here, to move all 7, right, it's moving 6, moving the 7th, moving the 6th again. To move 6, you move 5, move the 6th, move 5 again. To move 5, you move 4, move the 5th, move 4 again. It's just over and over and over. It repeats this pattern where it knows how to move 1, 2, 3, 4 by building up step by step by step. So moving 4 involves moving 3. Moving 3 involves moving 2. Moving 2 involves moving 1. And it just repeats this pattern. It's really like just fun to watch. So this one's easy to solve with recursion, harder to solve without it. So the solution for it here, Towers of Hanoi, Python, there's an easy solution here, is this. It's like 6 lines, right? Take your nth disk, your source pole, your destination pole, and the auxiliary, the storage, the extra pole. If it's 1, just move the 1. If it's not, move n-1 from the source and then flip the other way around here. Sorry, a couple more lines of code here. There it is. Right? Then, so move your n-1, move the 1 disk from source to destination, then repeat, flipped again. Right? So moving 3 is moving 2, moving the 3rd, moving the 2 back. Right? So it's move n-1, move the disk you want, move n-1, on and on and on. Excuse me. That's a quick recursive solution with Towers of Hanoi. Doing it without recursion here, Towers of Hanoi Python iterative solution is a little trickier here. You can do it though. I think, is this one that has the solution? Where is it here? No, I don't want to log in. No, thank you. Python. Yeah, it uses a stack here, this stack object to hold all that. Now, this is a lot more lines of code, right? Yes, you're all saying yes, right? Lots more lines of code. This one's no fun. So, all right, sorry, this took a little longer today than I was expecting. We'll call this good for recursion. Again, we'll come back to this next semester, go a little further in depth, look at some other ideas. Oh, I need some coffee. And we'll spend the rest of the time on our final project. Let me know if you have questions. If you get stuck somewhere, happy to help out. If not, we'll meet back on Monday. Excuse me. We'll talk more on Monday about plotting, have a quick lab, most of the lab time. Wow, that's really bad. And we'll go from there. All right, thanks, folks.